It is hard not to think of our immune defences in military terms. The host defence system has three elements. First, recognition systems that detect the invasion of something foreign. Second, the control and command systems which take that information and deploy and coordinate the weapon systems. And finally, there are the weapons themselves, the effector cells and the molecules that actually attack the invader. Human immune systems are incredibly effective. Without them, we would die quickly from overwhelming infections. Yet we still get infected. Why isn't immunity better? One reason is that pathogens have evolved a staggering array of methods to get round our immunity. That's unsurprising. Their very existence depends on their ability to break in. Pathogens do this by sabotaging all three elements of our immune defences. There are pathogens that try to avoid being detected. Some do this by camouflaging themselves with bits of host. Others hide in cells or tissues where immune surveillance is poor. Some even hide in the cells of the immune system themselves. Others don't worry about being detected. Instead, they change identity continually, a slippery moving target. I'll say more about this strategy in a moment because it's a very important reason why many diseases can't be controlled. And then there are pathogens that actively interfere with the command and control systems of immunity. What they do is produce molecules, or even induce their hosts to produce molecules, which interfere with the complex processes involved in regulating an immune response. Take worms, for instance. They can live in your body for decades or longer, even though they are often many inches in length and clearly very non-self. Some of them survive because they secrete substances which manipulate the immune response from weapon systems that are good at killing worms towards weapon systems that do almost nothing to harm worms. Other worms secrete substances that turn down the whole immune response. And then there are pathogens that attack the weapon systems themselves. Some eat or disable antibodies. Others produce toxins which kill immune cells, sometimes by making the immune cells commit suicide. Other toxins interfere with host cell movement. Others produce decoy molecules which distract from the real target, much like using flares to distract heat-seeking missiles. In fact, all of this attack and defense really is like an arms race. Pathogens evolve new ways to evade immunity, hosts evolve new defenses to that attack or new methods of fighting back, and this molecular and cellular warfare is ceaseless and ongoing. It is almost certainly the reason mammalian immune systems are so complex. Pathogens are always looking for weak points, hosts are always looking to try to shore up the latest breach. Okay, so that is the high altitude view of immune evasion. Now I want to talk to you a little more depth about those pathogens that evade immunity by changing their identity. These include some very important diseases like malaria, sleeping sickness, and flu. Host defense systems have to distinguish self from non-self. They do this by recognizing the molecules on the surface of pathogens or on the surface of the cell the pathogen is in, which is different from molecules which we produce ourselves. The molecules that are recognized by T cells and antibodies are called epitopes, and together the recognized molecules constitute the antigenic surface. Over 100 years ago, Paul Ehrlich, one of the founders of immunology, reported during his Nobel Prize lecture his work on African trypanosomes. These are single-celled parasites which cause sleeping sickness. He had discovered that what he called antibody receptors would disappear, even though the parasites were still there. We now know this is antigenic variation. The parasites have one type of surface coat, and just as antibodies against that coat are building up, the parasite's changing to a different coat and so slips away. And then just as the immune system is retooling to deal with that new coat, the parasite changes coat again and so on. This immune evasion strategy of constant coat change enables the parasites to persist for many months in a person. We now know an awful lot about how the parasites are able to change coats. They have a large number of genes coding for these coats, and they can turn them on and off at will. The parasites can even create new gene sequences during the course of an infection so that coat types can be continually generated even after the original repertoire is exhausted. This ability of the parasite to stay one step ahead of effective antibody control is why we do not have a vaccine against sleeping sickness. It is not a problem to induce antibodies against one coat, but to create antibodies against thousands of possible coats has so far proved impossible. This is also true for malaria parasites. Each parasite has 60 genes it can use to code for different coats, but it is not the same 60 for all malaria parasites. The repertoire in any population might be thousands. To my mind, the antigen repertoire of the parasites that cause malaria and sleeping sickness, how the repertoire has evolved, and how they are so carefully orchestrated, is one of the most fascinating basic science challenges in microbiology. Flu does things different. It changes things too. It changes continuously. You know that. It is the reason you need to keep vaccines against seasonal flu. A vaccine that is good one year doesn't work the next because the flu virus has moved on. It has acquired different antigens. But in contrast to malaria and sleeping sickness, it does not have a genetically encoded repertoire of genes to draw on. Instead, it changes surface molecules by mutation. The genes encoded its surface molecules mutate at random, like all genes, and sometimes the mutant antigen is sufficiently different that it is not properly recognized by antibodies directed against the product of the unmutated gene. When that happens, the mutant can escape immunity and so spread in the population. This is called antigenic drift, and it generates an evolutionary tree which looks like this: continual gradual change as a result of ongoing coevolution between the virus and our immune system. Flu can also do bigger, more radical changes called antigenic shift, which happen when different genetic segments of the virus reassort, generating new combinations of the N and H antigens that you hear about in the news: H5N1, H7N5, and so on. This happened in March 2013 in China, where a new flu virus appeared. This infects poultry and has so far cost over $6 billion and is not yet under control. In the first 3 months, the virus killed 36 people. It was able to get into people because it was a new strain and so able to get around the antibodies that humanity has to strains long past. Without that random genetic shuffle, the virus would die out. But with it comes the ability to evade our immunity. And that is why the 1918 Spanish flu was able to kill more people than died in the First World War.